Hello, welcome to Law of Conservation of Matter and Balancing Equations. So a little brief background of the Law of Conservation of Matter. This is that matter cannot be created or destroyed during a chemical reaction. This is very similar to the Law of Conservation of Energy, and essentially has to do with the fact that in our world, things don't just disappear or appear out of nowhere. All reactions have to be balanced to show a conservation of mass, energy, and charge. We don't balance much for energy this year, although we talk about it a little bit. We do balance for mass in this unit, and later in the year we'll balance for charge. In chemistry, we show our conservation of matter or our conservation of mass by balancing chemical equations. What's important to understand here is when we balance chemical equations, we're just making sure that anything that goes in comes out. Things will be rearranged, but they can't simply disappear. So in order to be able to balance reactions, we have to be able to count atoms. So when we look at a formula like calcium nitrate, we have to be able to see that, okay, there's one atom of calcium. This 2 is talking about all the stuff inside, so that tells us there's 2 nitrogens. And our nitrate group each has 3 oxygens in it, so this gives me a total of 6 oxygen atoms. So we should be able to look at a few different compounds and figure out how many of each atom we have. Please pause the video, and I'll put the answers up in just a minute. So we have 2 sodiums, 1 carbon, and 3 oxygens. 1 calcium, 2 chlorines, so that's going to that guy, and this is going to that guy to give us 8 oxygens. So this is the basics behind what we're going to need to be able to do when we look at a full reaction. Oops, sorry. And again, these are just a couple of examples if you need to pause the video and try these out if you didn't get enough practice. And there's the answers for those. So when we balance a chemical equation, we're going to be given a reaction, and you're going to notice in front of each of these, we have these little blanks right here. Those allow us to change what are called coefficients, okay? So we are going to be changing coefficients here. We will not be changing subscripts. Remember, subscripts are those little tiny numbers right there. So we want to make sure we're not allowed to change subscripts. Tell us how things are bonded together. We're not allowed to change how things are bonded in particular compounds. We can add groups of particular compounds, though. So and what we're going to do first is count how many atoms of each element we have. So we've got silver, nitrogen, oxygen, magnesium, and chlorine. Right now I have 1 silver right here, 1 nitrogen right here, 3 oxygens right here, 1 magnesium, and 2 chlorines. So these are my starting amounts. Then I'm going to go over to my product side. 1 silver, 1 chlorine, 1 magnesium, 2 nitrogens, and 6 oxygens. Now, some people ask, can we group the NO3 and balance those together? In this particular reaction, NO3 does stay together, so that would be an okay thing to do, but that doesn't happen in every single reaction. So in order to be consistent and make good habits, it makes more sense for us to separate those. So then we look and see what is not balanced here. So step 2, what elements are not balanced? Silver currently is balanced. Nitrogen and oxygen are not. Those numbers are not equal, and neither is chlorine. So we're going to pick someone to balance. I generally, as a rule, don't recommend starting with oxygen because of how the role that it plays in a lot of different reactions. My choice here would be to start with chlorine. If you wanted to start with nitrogen or oxygen, you could do that as well. You just have to remember they are in a polyatomic ion, so that can be a little bit tricky. So if I wanted to first worry about balancing chlorine, I only have 2 over here, or I'm sorry, I only have 1 over here, and I have 2 on the other side. So to fix that, I can throw a 2 in front of this group. So I now have 2 groups of AgCl. So it's going to turn this into a 2. It's also going to turn this into a 2. Now that did screw silver up, but we can fix silver later if that's not a problem. So now we fix chlorine, magnesium's still okay. We need to balance out silver, nitrogen, and oxygen. What's really nice is we need more of them over here on our reactant side, and we have the compound silver nitrate, which has all of those elements in it. By simply throwing a 2 right here, we have now made this 2, nitrogen is 2, oxygen is 6. So now we can check our work. Did we balance everything? So I've changed my coefficients. I recount my atoms. So I have 2 of each of these, 2 of each of these, 6, 1, and 2. Everything balances. I do have to check that I have my coefficients in a lowest whole number ratio. So I have the coefficient 2. This blank represents a 1. I have a 2 over here coming in front of AgCl and a 1 in front of magnesium nitrate. So I have indeed checked that my coefficients are in the lowest whole number ratio. They're not, you have to reduce them. So simple little equation here. We've got Li and N. So we start with 1 Li, 2 Ns, 3 Lis, and 1 N on the other side. You can pick either one of these to start with. I think lithium, or I think nitrogen might be a little bit easier. So if I put a 2 in front of lithium nitride, that will fix my nitrogen problem, turns lithium into 6, but that's okay. When we have something by itself on the other side, it's very easy to fix. So in order to have 6 lithiums on both sides, I can just put a 6 right there. I now have 6 lithiums, 2 nitrogens. My ratio is 6 to 1 to 2. So I am at a lowest whole number ratio. I'm going to do 2 more together and then we'll stop the video. So we've got aluminum, iron, and oxygen here. The reason I picked a single replacement reaction is sometimes there's some little math tricks you can use to make these a little bit easier. We start with 1 aluminum, 3 irons, and 4 oxygens on the left, 2 aluminums, 3 oxygens, and 1 iron on the right. What I like to do when I have a single replacement reaction, I have a little bit of a rule breaker on this one because it happens to be oxygen. I don't usually like to start with that, but I like to pick the thing that's always in the compound and go ahead and balance that first. Because once I balance that, balancing out iron and aluminum are going to be easy because they exist somewhere as free elements, so they're very fixable. Now, you can look at this a couple different ways. So what would I have to put here to balance out oxygen, or what would I have to put here to balance out oxygen? What's tough is when you look at each of these, there's no, if you put a 2 in one of them, it doesn't really fix it right away. So I like to think about how many oxygens I might end up with total. Since there's a 4 here and a 3 here, that gives me an idea that I'm probably going to end up with 12 oxygens. In order to end up with 12 oxygens, I'd put a 4 here, so it kind of relates to that 4 right there, and I'd put a 3 here. Let's see what that does for me. So that changes my iron to 9, my oxygen to 12, my aluminum over here changes to 8, and my oxygen over here changes to 12. So I've balanced out my oxygen now. Fixing iron and aluminum is really easy. I need 9 irons, and I need 8 aluminums. And you may be like, wow, those are big numbers. They are. But what we want to check for is really just if our coefficients are the lowest whole number ratio. We have a ratio of 8 to 3 to 4 to 9. There's nothing we can divide all of those by. So even though these are larger numbers, they're fine because they are in a lowest whole number ratio. Last one I want to go through with you is a combustion reaction. Combustion reactions can sometimes be a little bit trickier to balance, and there is a particular course that you want to take. There's a particular approach that can be very helpful with these. So we've got 8 carbons, 16 hydrogens, 2 oxygens. On the other side, we've got 1 carbon, 2 oxygens, and 2 hydrogens. A couple things to think about. Oxygen is in multiple terms. What I mean by this, it's here and here, so it's in multiple terms on the same side of the equation. That does not make it a good element to start with because you could accidentally balance it by putting something in the wrong place. So what I recommend starting with, the word combustion starts with a C, so I start by balancing my carbons. So in order to balance out my carbon, I'd say, okay, I'd have to put an 8 right here, okay? Now, that changes my carbon here to 8, which is great. Oxygen, I now have 8 times 2 is 16, and I still have this 1 right here. Now, one thing that should stick out to you about oxygen when you're thinking about this from a problem-solving standpoint is that there's a 2 there, which means we can't end up with 17 oxygens, okay? We're going to have to end up with an even number. We can only have whole number coefficients, so that's not going to work, okay? So this didn't really, solve our problem for us, but we still have some other stuff we could do. So we've got carbon balanced. Let's take a look at hydrogen. If we have 16 hydrogens over here, In order to balance that out, we can put an 8 right here. If we put an 8 right there, that gives us 16 hydrogens. It also changes oxygen, because now this represents 8 oxygens. So 16 plus 8 gives me a total of 24 oxygens, which is a lot, but that's okay. We've balanced our carbon, we've balanced our hydrogen, and oxygen's an easy fix. So if we want to put a number right here, we can fix just oxygen in one time. All we have to do is put a 12 there, and that gives me my 24 oxygens. Balanced, balanced, balanced. Let's look at our coefficients. 1 to 12 to 8 to 8. So we can't reduce this because that first coefficient being 1. This is actually the combustion of octane, and it's kind of an interesting reaction to look at, because when you see that 12 in front of O2, that tells you when we combust octane or fuel, gasoline for our cars, we're burning oxygen. And on the other side of that, we're producing carbon dioxide. So it's kind of an interesting tie-in to how we use some of our natural resources.